Hello everyone, my name is Gabo,
And I'm Miles.
and our project is called Naturwave. The objectives of our project is to assess the relationships between habitat quality and biodiversity in a highly fragmented and human-dominated landscape in Massachusetts. We're integrating spatial analysis, remote sensing, and soundscape ecology. Our study is part of a larger project conducted by Dr. Florencia Sangermano to advance the conceptual understanding of how landscape pattern and landscape pattern changes relate to biodiversity within a highly anthropogenically modified ecosystem. We hope to inform on the relationships and spatial metrics more useful to monitor biodiversity changes. In order to assess those relationships, we have created a package called Naturwave. Naturwave is a package that analyzes process sounds index data for NDSI, which is the Normalized Difference Sound Index that Miles will talk about later. It also assesses the correlation between sound indices and ecological variables of interest, taking into account different landscape metrics for Massachusetts at different scales of influence. The package also evaluates the importance of ecological variables at multiple scales and predicts NDSI values across the entire study area.
Thank you, Gabo. Just to comment on acoustic indices, the reason we're using them is that they allow an aggregation of acoustic signals to represent the overall acoustic community diversity of the landscape. What that means is we're using them as a proxy for biodiversity. Analyzing this gives us an idea about the biodiversity of the landscape, animals inside of there, so on and so forth. Now, we're using primarily in this study the NDSI, Normalized Difference Soundscape Index, which allows us to characterize soundscape properties such as to allow the identification of human influence of the landscape through the partitioning of soundscapes into biophony. So that's sounds from biodiversity, sounds from animals, nature, so forth, and anthrophony, sounds from humans. This allows us to classify a particular location based on its ecological and anthropic characteristics, gives us an idea about the human influence in the area. Now for NDSI, it breaks down similar to NDVI, and more common remote sensing indices. That'd be biophony minus anthrophony divided by biophony plus anthrophony. So as a result, you get values close to 1 when there's a lack of human influence, and a value close to -1 when there's a lot more human influence. The advantage to using sound indices and biodiversity studies is that's it's a less costly, reproducible approach to measurement analysis, and it allows us to contribute to the applications of remote sensing technologies and conservation planning and monitoring of habitat quality. Now, the data used for this study, as Gabo mentioned, Dr. Florencia Sangermano, she collected recordings at 11 different sites in Central Mass over the course of 3 months between June and August. These records total up to be close to over 1,200 taken during the day at these different sites in Central Mass. Once those, me and my research partner, Shrina, we processed those, brought them in, and were able to get the sound indice, NDSI values, along with some other sound indice values for them, which we'll talk about in just a second. But the other data utilized in this study is that of CAPS. These are separate landscape metrics taken in 2011 as part of a larger study by Amherst, Massachusetts, where they were trying to give a full biodiversity characterization of Massachusetts. 4 variables that we utilized came from their data. We brought them in as raw, then scaled them to make them easier to use, also reduce the size, and we cropped them to our area of interest here. Imperviousness and traffic are the human variables influencing the landscape, and connectedness and structure are the biodiversity elements influencing the landscape. Now, for our study, we brought these in, we analyzed the data, and this is we analyzed them against NDSI, and we we found that the highest Pearson correlation coefficient occurred at 2,500 meter buffer from the sample point going outward. That's a radius of 2,500 meters, mind you. That's where we found it was the most high. It had the largest impact and most strongest relationship with those other 4 variables that we just saw. Following that, in order to move forward with the project, create a predictive model, we had to then create a analyze the local, create a raster of those 2,500 meter buffers for those variables across the entire area of interest. We did that using focal mean, using the focal weight function here of 2,500 meters, specifying it as the buffer. Once we had those rasters, we were able to plug them into a random forest model, using it against the NDSI values that we had analyzed and wrangled together. And then from there, following analyzing the variables and points, we were able to do the predictive modeling. What we're looking at here is just the results of the preliminary work. So this is why we chose NDSI, because it was most highly correlated to NDVI, which allowed us that, and NDBI as well. And this allowed us to move forward with using NDSI as the soundscape metric and therefore the proxy for biodiversity. The other indices didn't hold up so well, so we moved forward with NDSI and their respective components. This just shows more about the relationship at the different buffers for NDSI and NDBI. As we go down here, we can see the peak values that we found within our own work for the 4 variables versus NDSI. Quite high correlation coefficient up here for Pearson's, and we see the peak values between 2,000 and 2,500 for the individual variables, with traffic coming in right there. These are the raster results from the focal mean analysis. They turned out how we were hoping. They're on the scale. They're scaled down. As we can see, imperviousness values are representative of Worcester. Perviousness, NDBIs, think like NDBIs values, heavy structure, human influence, seeing Fitchburg, Worcester there, structure, vegetative structure, we're seeing a larger area. And those were our results that we used for a predictive model.
We use random forests to evaluate the variables and find out their order of importance at predicting NDSI values. These results reveal that traffic and imperviousness are the variables with a higher explanatory power at predicting NDSI values across the study area. The mean square error graph on the left indicates that traffic has a prediction ability of 9.61 approximately, and imperviousness has a prediction ability of 6.69. These are the highest values compared to the other 2 variables. So these are the variables that will influence NDSI prediction more than the other 2. Next. The results from modeling is a predicted surface of NDSI values across the study area on a scale of 0 to 1, which high NDSI values will be away from traffic and impervious locations. Next. So we assess the relationship between habitat quality and biodiversity in a highly fragmented and human-dominated forest landscape in Massachusetts. It was expected that ecological variables such as imperviousness and traffic have a much higher degree of influence at predicting NDSI values compared to connectedness and vegetative structure. The NDSI predictions results are highly reasonable, and they correlate well with the 4 ecological variables of interest. In urban landscapes, imperviousness often decreases the habitat for species distribution, and it also leads to habitat fragmentation, which causes a decrease in habitat connectivity, affecting the range of continuous movement of species across the landscape. As we have found in this study, NDSI values are higher as we move away from sampling locations, and they are best at approximately 2,500 meters, which was identified as a scale of best influence. In the future, more variables should be tested, such as ecological integrity and microclimate alterations. And it's also good to validate the results of our predictive modeling with fieldwork data, which we're hoping to do in the near future. And also to assess the capacity of models to extrapolate the relationships between habitat structure and acoustic diversity. Thank you.
Thank you.